Let us now formally define linear feedback shift register. So as we have said, the linear feedback shift register of length L consists of L stages number 0, 1 to L minus 1. Each stage capable of storing one bit, either 0 or 1, and having one input and one output, and a clock which controls the movement of data. And during each unit of time, these three operations are performed. The content of stage 0 is output. It forms the output. It forms the part of output sequence and forms a part of output sequence. Okay. So stage 0, content of stage 0 is output and forms the part of output sequence. The content of stage I is moved to stage I minus 1 for each I from 1 to L minus 1. If you see the figure, this is stage 0, stage 1, stage L minus 2, stage L minus 1. So this is an LFSR of length L. And this stage 0 output of stage 0, essentially the content of stage 0 essentially forms the part of the output sequence. And the content of stage I, stage 0, content of stage I is moved to stage I minus 1. So the shifting is like that. Stage L minus 1 is moving to stage L minus 2. Stage 1 is moving to stage 0. Okay, from stage I, data is moved to stage I minus 1 for each I lying between this interval 1 to L minus 1. And the new content of stage L minus 1 is the feedback bit Sj, which is calculated by adding together modulo 2 the previous contents of a fixed subset of stages 0, 1 to L minus 1. Okay, so this Ci, this C1, C2, Cl minus 1, Cl, these are either 0 or 1. Each of them is either 0 or 1. So if you take this is 0, then essentially this is not taken in the XORing. If it is 0, then output of this AND gate is 0. So it will not contribute in calculating this feedback bit. If it is 1, then it is contributing in forming the feedback bit. This is the idea. Okay, so this C1, C2, Cl minus 1, Cl, this passes through the, so this together with the stage 0 output passes through an AND gate, and at output is XORed. Every output of this AND gate is XORed. So this XOR value, in this XOR value, this stage value, this bit contributes provided this C, corresponding C is 1, and it will not contribute means it contributes in forming this feedback bit. So that is why it is we are saying new content, this Sj at the stage L minus 1. So new content Sj, this is the feedback bit Sj, which is calculated by adding together modulo 2 the previous contents. This content, previous contents of a fixed subset of stages 0, 1 to L minus 1. So some fixed content means from this stages, the value stored in these stages, a finite subset of this is taken, depending on whether Ci is if C1 is 0, then it will contribute to the feedback bit, otherwise it will not contribute. So this is how the linear feedback shift register operates. This Ci is either 0 or 1, and this essentially this is an AND gate. This is an AND gate. Okay, Sj is the feedback bit. And it is calculated taking modulo 2, that means XORing. So modulo 2 sum of the content of those stages I for which Ci is Cl minus I is 1. Okay, so for this with the stage L minus 1, C1 is connected. Stage L minus 2, stage C2 is connected. So for stage for stage I, Cl minus I is connected. Okay, if Cl minus I is 1, then the stage I corresponding value contributes into the feedback bit formation. Okay. Now we define LFSR. This LFSR is represented by this L, CD. L is the length of the LFSR and CD is the connection polynomial. So CD, how I define the connection polynomial? So connection polynomial for this is defined to be CD equal to 1 plus C1 D. See, this is a polynomial in the indeterminate D. This D is a variable. Okay, so we consider the connection polynomial corresponding to this is 1 plus C1D plus C2D square plus CL D to the power L. Okay, so if it is stage L minus 1, it is C1. Stage L minus 2, it is C2. Stage 0, this is CL. So CL D to the power L, and here 1 plus C1 D C2 D square CL D to the power L, like that. So this is an element of Z to D. So this notation represents a polynomial in the indeterminate D. Polynomial in the variable D whose coefficients are from the field Z2. That means the coefficients of the polynomial are either 0 or 1. So this is an L degree polynomial, and this element belongs to Z2D. This is the collection of all polynomials of degree, all polynomials of any degree. The only restriction is the coefficients are from Z2. The coefficients of those polynomials are either 0 or 1. So these CIs, any polynomial you take, the CIs, the coefficient CIs are either 0 or 1, and D is a variable. Okay. So this is called connection polynomial. So if your LFSR is like this, then the connection polynomial is C1 plus C1 D plus C2 D square plus CL D to the power L. Okay. So LFSR, generally we will denote an LFSR by this, by specifying its length and by specifying the connection polynomial. The connection polynomial is a degree L polynomial. Okay. And we say that an LFSR is non-singular if the degree of the connection polynomial, this degree is L. Non-singular polynomial, non-singular LFSR means the degree of C, D should be L. That means the CL is 1. If CL is 0, then degree of the polynomial is not D, it is less than it is not L, it is less than L. So CL is taken to be 1 in case it is a non-singular LFSR. Now, if the initial content of stage I is SI, initial content of stage I is SI. SI is 1 bit. Means every stage here is essentially one register that can store 1 bit, either 0 or 1. This holds either 0 or 1. This holds either 0 or 1. This holds either 0 or 1. So if the stage I, the content of stage I, initial content of stage I is SI, which is either 0 or 1 for each I lying between 0 to L minus 1, then this SL minus 1, SL minus 2, S1, S0 is called the initial state of the LFSR. So initially it holds SL minus 1, it holds SL minus 2, this holds S1, this one holds S0. So this is called initial state of the LFSR. So LFSR is specified by its length, its connection polynomial. If it is non-singular LFSR, the connection polynomial should have degree L. That means CL not equal to 0. This is 1. And the content, the initial state, what is the initial state of LFSR? The initial content of the registers in the L registers in the LFSR is called the initial state of the LFSR. Now, if the initial state of the LFSR in the figure is suppose SL minus 1, S1, S0, then the output sequence, the key stream will be this S0, S0. So initially this is SL minus 1, SL minus 2, S1, S0. So this S0, SL minus 1. Okay. So when it comes here, it shifted here like that. So initial output sequence part is S0, then S1 comes, then S2 comes, SL minus 2, SL minus 1 like that. Okay. SL minus 1, and these are uniquely determined by the following recurrence relation. Sj is simply C1 Sj minus 1 plus C2 Sj minus 2 plus Cl Sj minus L modulo 2 for j greater or equal to L. So initially it is S0, S1, S2, SL minus 1, and when you take L, j equal to L, it starts from this, by this recurrence it gives the values of Sj for j greater or equal to L. So if you calculate SL, it is essentially the SL is C1 SL minus 1. So you are taking AND of C1 and SL minus 1, then AND of C2 SL minus 2, AND of CL L minus L means 0. Okay, C1 SL minus 1, C2 SL minus 2 like that. Okay, and you take modulo 2, means these are plus, means essentially this operation is modulo 2. Okay, so this is how it works. This recurrence is given by this. So this is hardware implementation of generating pseudo-random bit string. This example already I have discussed. You can go through this. In terms of connection polynomial, this is essentially the previous example. In the last class I have discussed this, and it is given by this 4, comma, the connection polynomial here is 1 plus d to the power 4. Okay. So if this is D0, this is your D0, this is D1, means stage 0, stage 1, stage 2, stage 3, then connection polynomial, if 1 plus d to the power 4 is your connection polynomial, then coefficient of this comes here. It is connected, it is actually ANDed with this stage. So so this is 1, the coefficient of yes, C1 comes here, C2 comes here, C3 comes here, C4 comes here. Now you can see that in this connection polynomial, C1 is 1, so essentially this is contributing in the generation of the feedback bit. And C4 is also 1, this is also contributing. But C2 and C3, the coefficient of d square and d cube, these are 0, so it will not contribute, it is not tapped here, So the recurrence is given by Sj equal to Sj minus 1, Sj minus 1 and Sj minus 4. Sj is given by, means this is simply C1 and C4 coefficients will come, C1 and C4. So C1 is 1, so this is Sj minus 1, and C4 means Sj minus 4. Okay, J minus 4. Okay, so if your initial state is all 0, then only 0 sequence you will get as your output. So if the key stream is initiated with any vector other than all 0, then we obtain a key stream of period 15. Already we have checked that. Okay, so this is discussed here. You can just go through it once again. Same thing we are doing. This is illustrated. It's from, if it is first, initially it is 0 1 1 0, suppose. Okay, I have taken 0 1 1 0, and after completion of 15 step. In the 16th step, it is giving you 0, 0, 1, 1. That means at the initial position, you are again in the initial position. So everything will repeat. You are getting output. So this is your D0 part is your output sequence. D0 part, this D0 part, this is the part of output sequence. So this is your output sequence. Okay, output sequence, and it is having period 15. Okay, so I have written here it satisfies Goulomb's randomness postulates. What are Goulomb's randomness postulates? We will give those. We will discuss those things. Okay, so this is another example. A connection polynomial is different. This is also a 4-length LFSR, but the connection polynomial is now 1 plus dq plus d to the power 4. So C4 connection is there and C3, that means this. So if I write this one is giving the part of output, then C4 is here and C3 is here, and C2 and C1 are 0. So essentially, in the formation of Sj, the feedback bit generation, this one and this one is contributing. Okay, and the recurrence will be simply Sj will be Sj minus 3 and Sj minus 4 plus XOR. So modulo 2 operation. Okay, so here also you can check that key stream you are getting this, and after 15 steps it is repeating, because I have considered initial vector to be 0, 0, 0, 1. I started from here. Okay, so some more facts about this LFSR. Okay, so this is it says that any other non-zero vector, any other non-zero initialization vector will give rise to a cyclic permutation of the same key stream. So it says that here you can see that I have taken the initial vector to be 0, 0, 0, 1, and I get the output sequence to be this sequence, this D0 output, D0. Okay, and if instead of this initial vector, if you start with any other initial vector, then you will get same key stream, cyclic permutation of the same key stream. Cyclic permutation of the same key stream. Suppose I start with 1, 1, 1, 1. Okay, 1, 1, 1, 1. Then I will get from here. So this is cyclic shift of this entire thing. So this will come first, then the above will appear. So it is a circular shift. It's a circular permutation we will get. Okay, so another fact is that every output sequence for all possible initial states of LFSR of length AL is connection polynomial CD. This is periodic if and only if the connection polynomial CD has degree L. Okay. So that means it is non-singular LFSR. So the LFSR L, CD is periodic if and only if it is non-singular. That means connection polynomial CD is having degree L. That means the coefficient of highest power d to the power L, that coefficient d to the power L coefficient is C0. Coefficient is CL, right? CL. Coefficient is CL. Yes, coefficient is CL. Let me see. Yes, here. Yes, this one. CL is non-zero. Connection polynomial CL d to the power L. No? So CL is non-zero, then it is non-singular. CL is non-zero, it is non-singular. Okay. The another thing is, so we have just without proof I am just stating these things. Okay, LFSR periodic if and only connection polynomial means this LFSR is non-singular, and this LFSR if it is having degree L, does not mean it will always have a period. It is periodic, but its period may not be always 2 to the power L minus 1. Whatever examples we have taken, it was always 2 to the power L minus 1. L I have taken to be 4, so it was both the examples. For both the examples, it was 15 2 to the power L minus 1. But it is not always the case. So the fact that we have, if n is the period of an LFSR, L comma CD, where CD is having degree L, that means CD having degree L means it is periodic, period is n, then if CD is irreducible, then CD must be irreducible. Okay, CD must be irreducible. If CD is irreducible, then this n is a divisor of 2 to the power L minus 1. So period may be smaller than this, but it is always a factor of 2 to the power L minus 1. N must divide 2 to the power L minus 1. This can be proved. Okay, these things can be proved. But here we are not going to discuss those proofs. These are number theory stuffs. Okay, so we are not going to discuss those things. So the period may not be 2 to the power L minus 1, it can be less. And if it is less, then it is always a divisor of 2 to the power L minus 1. And when it will be exactly 2 to the power L minus 1? 2 to the power L minus 1, when this CD, this is irreducible polynomial, when this CD irreducible, it is also a primitive polynomial of degree L. If it is a primitive polynomial of degree L, then the period of the LFSR will be exactly 2 to the power L minus 1. So we get maximal length LFSR. This is called when your period of your LFSR is maximum 2 to the power L minus 1, maximum period. We say it is a maximal length LFSR. And the output of this output sequence is called M sequence. It's maximal length is a maximal sequence, maximal period sequence. Okay, so the output sequence is called M sequence. Now, what we mean by primitive polynomial, this is also means if you have gone through group theory, you must know that what is a primitive polynomial, a primitive element, essentially a generator of a cyclic group, multiplicative cyclic group. So essentially what happens, if a primitive polynomial means, we consider this field, CD is a primitive polynomial. First condition, it should be irreducible. So an irreducible polynomial, if you take this thing Z2D divided by CD, this is a field of 2 to the power L many elements. Okay, so what do we mean by this? Z2D, as I explained, Z2D is the set of collection of all polynomials with coefficients from Z2. Coefficients of these polynomials are either 0 or 1. Okay, so this is a collection of all polynomials. Now we divide all those polynomials by this L degree polynomial. So how many means then all these polynomials now, initially these were all polynomials. Now I divide by a L degree polynomial. Divide L degree polynomial and take the residue. Okay, so when you divide by L degree polynomial, every polynomial is divided by L degree polynomial, its degree reduces to maximum L minus 1 now. So because every polynomial is divided by a polynomial of degree L. So every polynomial in this class having degree at most L minus 1. It is less than L. Okay, so you can prove that it is how many polynomials you can get. This is a finite set. So individually, if you consider Z2D, it is an infinite set. But when you divide every polynomial in this infinite class of polynomials by a degree L polynomial, it becomes a finite set. And it can also be proved that this finite set is a field having 2 to the power L elements. These are all abstract algebra things. Okay? Or number theory also we study all these things. So this is a field. And if you consider, so the field means we have two operations, plus and dot means multiplication. So the multiplicative group that actually forms a cyclic group. Multiplicative group is a cyclic group, and cyclic group means it has a generator. So that generator, so this is a primitive polynomial if its generator is a root of this. Okay, so if alpha is a generator of this field, alpha is a generator of this field, then that generator is a root of CD equal to 0. That means D equal to alpha. Alpha is a generator of this, means every element, every non-zero element of this can be written as powers of alpha. Alpha 1, alpha square, alpha to the power 0, alpha square, alpha to the power alpha square, alpha cube, like that. Okay, so this is a cyclic group. Multiplicative group is a cyclic group. It has a generator. Every element of this field except 0 can be written as powers of that alpha. And this is called primitive polynomial CD, by which you are dividing, you are forming, that helps you to form this field. If its root generates this, then this is a primitive polynomial. I hope you have understood this. Okay, so D equal to alpha is a generator of this field except 0. This star means essentially 0 I am excluding. The cyclic group, the multiplicative group of this field, this multiplicative group means 0 is excluded. That multiplicative group is generated by a root of CD equal to 0. Then CD is a primitive polynomial. Okay. Okay, so this concept essentially we need later also. Okay. So what we learned, what we have learned, LFSR of length L, connection polynomial CD. This is periodic provided CD is non-singular. That means degree of CD is L. Now period of this LFSR of length L may not be always 2 to the power L minus 1. Whenever it is 2 to the power L minus 1, we say it is maximal length LFSR. And under what condition it will give you maximal length LFSR? Under this condition. This CD connection polynomial should be a primitive polynomial in this sense. Okay, in this sense. So maximal length LFSR is possible provided you choose your connection polynomial to be a primitive polynomial. That means its root, one of its root, it is algebraic polynomial. One of its roots must be a generator of the cyclic multiplicative group of this field. It will generate every element. It will generate every element of this field except 0. So every element of this can be written as powers of alpha. Alpha is a root of this. CD equal to 0. Okay. Now, so we have few more facts here. The first one, suppose we have an LFSR, CD is connection polynomial of degree L. If CD is irreducible over Z2, CD is a connection polynomial of degree L, coefficients are from Z2. It is irreducible over Z2. If it is irreducible over Z2, then each of the 2 to the power L minus 1 non-zero initial states of the non-singular LFSR produces an output sequence with period equal to the least positive integer n such that CD divides d to the power n plus 1. Okay, so here means if it is irreducible, its period is n, then n is essentially determined in this way. This is the least positive integer such that CD is a divisor of d to the power n plus 1. Okay, so it is always the case that this n is a divisor of 2 to the power L minus 1. it can be proved. We are not going to discuss the proofs here, okay, because this is not a number theory course or abstract algebra course. So this n, the period, this n is essentially the least positive integer such that CD divides g to the power n. CD divides g to the power n plus 1, and this n divides 2 to the power l minus 1. It actually follows from this fact. So if the CD is irreducible, then this happens, that the period means this is essentially the period. It is the least positive integer for which CD divides g to the power n plus 1, and consequently n divides 2 to the power n minus 1. In case CD is primitive polynomial, irreducible primitive polynomial, it is irreducible, but along with that it has that extra feature, means it generates the multiplicative group of f2 to the power l except 0. Okay? So if it is irreducible, if it is primitive polynomial, then each of the 2 to the power l minus 1 non-zero initial states of the non-singular LFSR LCD produces an output sequence with maximal possible period 2 to the power l minus 1. So whatever we have explained earlier, it is written formally in here. If it is irreducible, then period divides 2 to the power l minus 1, and not only period, but CD essentially divides g to the power n plus 1, where n is the least positive integer. Okay, that satisfies this condition. And if in case it is primitive polynomial, then we get the maximum possible period 2 to the power l minus 1. This one is okay. So M sequence I am defining here maximal length LFSR. If CD is a primitive polynomial of degree L, then LCD is called a maximal length LFSR. Because if it is primitive polynomial, then this is maximal length LFSR, maximal period we get 2 to the power L minus 1. This is the period length. Okay, so we get maximal length LFSR. And output of maximal length LFSR with non-zero initial state is called an M sequence. So here we formally define what is maximal length LFSR, what is M sequence. Okay. So this fact, mentioning this fact here is essentially unnecessary. Means it is not unless I explain you the Goulomb's randomness postulates. So when we state this Goulomb's randomness postulates, or what properties this pseudo-random function, pseudo-random sequences should possess, I will maybe I will come to this again. Let us just mention it here that this M sequences, why we are discussing these M sequences having some nice statistical properties. So if S is any M sequence is essentially that maximal length that means if you start with initial state, non-zero initial state for a maximal length LFSR, then you get output sequence that is essentially your M sequence. And this M sequence is how what is the length of M sequence? 2 to the power L minus 1. Okay, so the M sequence it has nice statistical properties. It satisfies Goulomb's randomness postulates. We will discuss those. Not only that, if you fix any integer between 1 to L, any integer k between 1 to L, and you take S bar any subsequence of length, this particularly of this length. So this S is having this S and this S should be same. Okay, so this S is having length 2 to the power L minus 1, maximal period length. Okay, and if you fix any k in between 1 to L and you take a subsequence of this S bar is the subsequence of length 2 to the power L plus k minus 2. Okay, then we have some nice features. For every non-zero sequence of length k, means each non-zero sequence of length k appears exactly appears exactly 2 to the power L minus k times as a subsequence of S bar. So this is essentially a pattern. This a particular pattern, how many times it will come in the subsequence. Okay, so it says k is 1 to L, S bar any subsequence of length 2 to the power L plus k minus 2. You take any subsequence 2 to the power of length this. Then each non-zero sequence of length k, each non-zero sequence of length k, that means length k, any non-zero sequence you pick. It is a pattern. It is a pattern of 0, 1, some pattern of length k. So that pattern will appear exactly 2 to the power L minus k times as a subsequence of S bar. If your S bar is having length 2 to the power L minus L plus k minus 2. So this feature, this M sequences exhibits these features. Okay, so pattern, how many times that particular pattern will come. So we will, when we will discuss the statistical properties of pseudo-random functions, we will come to this. So these are some tests that are very much essential for a sequence to be pseudo-random sequence. Furthermore, the zero sequence of length k appears exactly 2 to the power L minus k minus 1 times as a subsequence of S bar. So what we mean to say, the distribution of patterns having fixed length of at most L is almost uniform. So a particular pattern is almost uniformly distributed throughout the sequence. Fixed length, having fixed length of at most L is almost uniformly distributed, each pattern. Okay, k you can vary from 1 to L. So k you can take 1, so one length pattern you take, 2 length pattern, L length pattern, maximum L length pattern, and their appearance, the distribution of a particular pattern is almost uniform. Okay, so these are the properties of LFSR. A primitive polynomial, more formally it is defined here. Okay, it's more formally we have defined here PBA prime, distinct prime factors of p to the power m minus 1 be r1, r2, rt. Then an irreducible polynomial fx belongs to zpx. Suppose fx is you take a polynomial of degree m, it belongs to zpx for, well, in our case, in our discussion, we have taken p to be 2. So it holds for any prime. Okay, so if you take any irreducible polynomial, if it irreducible polynomial means that cannot be factored. I haven't mentioned that irreducible means that cannot be factored. Okay, so 1 and fx is the only factors of this. So fx belongs to zpx is primitive polynomial if and only for each I from 1 to t, means I means this ri, r1, r2, rt, this I from 1 to this I running from the suffixes of this r, x to the power p to the power m minus 1 divided by ri. Okay, so this is not congruent to 1 modulo fx. This is not congruent to 1 modulo fx. So these ri's are essentially all the factors of p to the power m minus 1. So if you so it means that x to the x is x order of x is p to the power m minus 1. Order means order, if you remember what we mean by order, order of an element means x to the power is, this should be the least positive integer, n should means k is order, suppose order of x, that means k is the least positive integer such that x to the power k is congruent to 1 modulo fx, something like that. Order modulo fx, what we mean by order of x modulo fx, x to the power k should be congruent to 1 modulo fx. So it means that the order of x cannot be less than this. So if you all the means p to the power m minus 1 by ri from 1 to n, you checked all of them and it is not giving you 1 modulo fx. Modulo fx means this is minus 1 is not divisible by fx. So when you take 1 this side, so you get a polynomial x to the power p to the power m minus 1 by ri minus 1. So when you divide, so this polynomial is, you have to show this polynomial is not congruent to 0 modulo fx. So fx does not divide this minus 1. So if you take the factors, if you keep on dividing this p to the power m minus 1 by its factors, distinct prime factors, then this one is not divisible by fx. So maximum means p to the power m minus 1 is the order. This is what we mean to say x is element of order p to the power m minus 1 in the field this. Okay, in the field this. Get px, set of all polynomials, coefficients 0, 1 to p. Coefficients are zp, modulo zp, coefficients are 0, 1 to p minus 1. So all polynomials, coefficients from 0, 1 to p minus 1, and you take modulo fx. Fx is a polynomial of degree m. So how all the elements here are essentially polynomials of degree at most m minus 1. Okay, or at most m minus 1. So how many elements you have here? How many elements you have? P to the power m minus 1. So first element is 0. This is essentially field. First element is 0, and if alpha is the generator of the multiplicative group, all the elements are alpha, alpha square, alpha to the power m minus 1. And this alpha is the generator. Okay, so order of alpha is p to the power m minus 1. Okay. Primitive polynomial, to check, this is essentially a checking procedure. How to check whether a polynomial of degree m is primitive or not. So you take all the factors of p to the power m minus 1, distinct prime factors, and this checking is sufficient. This is also can be proved. In number theory, we prove these things. So this is the checking of whether a given function is primitive polynomial or not. Okay. Okay. So LFSR, this I will cover later. Okay. Okay. Let us stop here.